Okay, questions on the homework? Appendix B.
Oh no.
30.
30. What is that?
Is sigma notation. The top is n, bottom is I equals 1, and 2 minus 5, 5.
2 minus
5, 5.
5, 5. Okay. What was the question? To evaluate?
Yeah, fine. Yeah.
Right, so I would use the fact that we can distribute across sums. So this is just sigma I equals 1 of 2 minus, and I can also factor out that constant 5. Right, so now I know what this is, right? It's a constant, so it's just a constant times n. 5 times the sigma of I, we know what that is, that's n times n plus 1 over 2. And that's it. Good.
Well, you don't have to simplify.
I wouldn't particularly care to simplify.
Because on the website, we have to be telling you all these.
So write it in what form?
In like one single.
Like a polynomial?
Yeah.
So 2n, this is minus 5 over 2 times n squared plus n. So this is 2n minus 5 over 2n squared minus 5 over 2n. I'm going to combine these two n's. So this is minus 5 over 2n squared. And this is 4 over 2 minus 5 over 2 minus 1 over 2n. So you can write it like that, or you can write it as something like minus 1/2 times 5n squared plus n. Or minus 1/2 n. Either of these are acceptable to me, like from here to stop here, as far as I care.
Can I ask a question?
Yeah.
Can you do it at all of the whole S thing we taught us at the very beginning?
The what?
Remember S equals something and then 2S equals something divided by 2? Like,
You
remember?
could have done that here, but I would have probably only done that with this part. This part you realize is just 2 plus 2 over. You're adding that over and over n times. So that one would be easy to figure out. This one you could have done that trick where you added it in 2 directions and you would get. But you knowing the formula makes it easier for us.
Is this on the test?
Huh?
Is this on the test?
Other questions?
You got 35, right? Is it 35?
Yeah, 35.
What is 35?
Simulation n. So I is equal to 1.
I equals 1 to n
I cubed minus I minus 2.
minus I minus 2. So you want to evaluate that?
Yeah, I just don't really understand the simplified stuff.
Oh, well, this again, you know you can distribute across sums.
Yeah.
So this is just, I go from 1 to n of I cubed minus, go from 1 to I minus. So this we know is n times n plus 1 over 2 squared minus n times n plus 1 over 2 minus 2n.
Can we leave it at that or?
Yeah.
Okay.
So we have n squared, n plus 1 squared. Could factor out the common n and a half, yes. Although this is a quadratic. But, and over 2. certain way they wanted to calculate. Or something like that. Just multiply this out and write it out. Would whoever signed complain if you put that in? Or
Yeah.
did you actually try it and not complain?
I didn't, well, this question I just didn't do on the website yet,
Okay.
but like all the other ones.
Well, I would have expanded this, you know, n squared plus 2n plus 1, expand the n, and just come back. That's not the important.
Because I know that like the I squared question, they made you actually put it all into one column.
Yeah.
Okay, but on the side on the web, from the website, segmentation I equals 4. On the top of 8 and
It's what?
top of the sigma notation is 8.
8.
And the equation is 4i minus 2.
4i minus 2.
Yes.
Okay. So for this one, there are only 4 terms, so you can actually write it out. You could brute force this one. No mercy. Right? You just literally write this out. So it's 4 times 4 minus 2 plus 4 times 5 minus 2 plus 4 times 6 minus 2 plus 4 times 7 minus 2 plus 4 times 8 minus 2. And you just compute the answer that way. But of course, if these numbers had a huge gap between them, like it's 4 to 500, then you wouldn't want to do it this way. The trick would be well, it's not really a trick, it's just like an observation. It's to notice that if you sum from 4 to 8 of some function, it's actually the same as summing from 1 up to 8 of the function, and then subtract the sum from 1 up to 3. Right? So I take the sum of the first 8 terms, but then I kill the first 3, so that I get the sum of the 4th term onwards. Right? So that's sort of the idea. So this sort of comes from the idea, if I have the sum of I goes from 1 to 8 of an minus I goes from 1 to 3 of an, then this guy would give me a1 plus a2 plus a3 plus a4 all the way up to a8. And then this guy, I would subtract a1 plus a2 plus a3. Right? So then, and I'm left over with the one that goes from 4 to 8. Right? That's the idea. So this one, now to go back to this example. If I did I goes from 1, 4 up to 8 of 4i minus 2, I could just think of this as 1 to 8 of 4i minus 2 minus 1 up to 3 4i minus 2. This one I can split up. This is just 4 times the sum of I from 1 to 8 minus the sum of 2 minus 4 times the sum of I from 1 up to 3 of I minus the sum of 2. These guys would die. This guy is 4 times 8 plus 1 over 2 minus, this would be 4 times 3 times 3 plus 1 over 2. So that cancels 2, this cancels 2. So this is 60 times 17 minus 6 times 4. That's what Yes.
Well, number 25, right, it's signification 20 and on the bottom n equals 1 and then -1 to the n power. So for that one it's easy because -1 to the first to the second, whatever, it's always going to be either -1 or 1. But what if it was harder? What if it was a different number and you didn't know what value would be every step of the way? You can't write it out for 20 numbers. What else would you do?
You just notice the pattern that after every even guy, you get 0. Right? Because you'd have a -1, then a +1, then a -1, then a +1, then a -1, then a +1. Which means every pair gives you 0. Which means if you're adding an even number of them, the answer would be 0. If you're adding an odd number of them, it's going to be either plus or -1 basically.
Well, what if it was like a positive number? Like 4 to the first and 4 to the second and 4 to the third, up to 20. You'd actually have to do it out up to 20?
There's a formula for it, but you don't have to worry about it. In Calc 3, you're going to learn about something called the geometric series, which will answer that. You won't have to worry. Yeah.
I really don't understand what you did, like, under method 2.
This is saying I want to add all the guys from the 4th term to the 8th term. So what I did was I added from the 1st term to the 8th term and then subtracted the first 3.
Alright.
Get the first
Right.
Yeah, I get it.
Huh? I subtract the first 3 because I want to start at the 4th, right? So it means I pretend there are 8 guys, 1, 2, 3, 4, 5, 6, 7, 8, but I only care about these. So what I do is I add all of these and then subtract these to get those. And the reason why I did that is because I have a formula that tells me how to deal with it when there's a 1 here, right? So then I want to use that to my advantage. I don't have a formula for when there's a 4. So I sort of use this idea so I can apply these formulas to each of these.
The formula doesn't work when it's not.
No, the formulas do not work if it's not a Yes, formulas are very specific. Right? If it could work for any number, I would have given you the formula with like I equals A or something like that, right? But I said I equals 1, it has to be 1 for the formula to work. I don't think we can finish 4.1 in the time we have left, but I think at least I want to do an illustration to give you an idea of where it's going, and maybe we can do some simple examples.
We can't finish it.
So let's go to an example that we had from the beginning of class. We did something similar to this. Remember when we had a distance function? Say it's s of t equals, I don't know, 2t, something easy so you can see the idea, right? And so what I could do is I could plot this where t is time in seconds, s is
Already still doing sigma
in meters, right? So if I plot s versus t, that would be the graph, right? Going up to some point, I don't know, but that's the graph. Now, we said we could measure the slope of this graph, and the slope was equal to what? The slope of s is equal to 2, i.e. The velocity, right, which we know is the rate of change of position. Right? And now what we did with derivatives is we tried to have a formula that gave us the slope in general. And we could actually treat this formula as a function in its own right, right? So this gives another function called v of t, which we know is the derivative Now, if I actually plotted that function, what would that look like? Well, it's just a horizontal line, right? Now, here's a question. What is the distance traveled between t equals 1 and t equals 2? What will be the distance traveled? Well, there are several ways you can do this, right? You can subtract the position function, right? Just find out what is my distance at 2 subtracted the distance I was at 1, at 0, at 1. Right? That's one way to go about it. Right? So I can go here, I know when time is 1, my value is 2. When time is 2, my value is 4. So then the distance I traveled was 4 minus 2. 2 meters, right? But notice something else. What if instead I look at the area under the velocity curve? So here, 1, here, this is 2. So look at this area. I know that this height is 2, right? What is actually the area under that curve? It's a rectangle, so it's just length times width, right? The answer is 2 times 2. Times 1. Because it's 2 minus 1, which is 2.
Hold on, I get the second one.
Come again? What did you say? What's that?
The area
Under the velocity curve.
how'd you get that? Oh, you've done spike.
It's a rectangle, right? This is just a horizontal line, and I'm looking at the area between 1 and 2. Right? So it's just a rectangle, length times width. I also get 2. And you can try this with a bunch of different numbers in this example, and you realize the area under the velocity curve is always going to give you the distance traveled in that interval. Right? Turns out it's not a coincidence, this always happens. Right? The area under V of t on the interval I is actually equal to the distance traveled on I. In other words, in this case anyway, the area under the derivative of s gives the distance, the antiderivative of s. Or I should say equivalent in some sense. Right? Basically, I can use the area under the velocity function to tell me about the position function. Right? Did you notice that that's essentially what I could do? I could look at the area under the derivative of s to tell me about the values of the original s in the first place. So even if I didn't know about this function, and you only gave me, this is the velocity, right? Figure out, tell me about the distance function. Tell me about s. Well, you can always know that if I look at the area here, it tells me about the function there. But what is the function over there? It's the antiderivative of this function. So somehow the area of a function is sort of equivalent to its antiderivative. We know that to get from v to s, we have to take an antiderivative. But looking at the area under v actually does the same thing. in some way, right? It gives me the difference between two values. But it stands to reason that we can sort of generalize this, that somehow antiderivative and area sort of go hand in hand. And somehow the area under a curve is sort of like reversing the derivative. This is the whole idea behind, well, the fundamental theorem of calculus. Yeah.
Isn't it just like the critical point, how we find out the first derivative and the original?
Just the critical points? What about that?
Yeah, like you find the point on the curve, the local maximum is from the first derivative.
Yeah.
They work in the original. Something like that.
Not exactly. I'm talking a lot more general here. I'm like saying that if I could find a formula that gave me the area under the velocity curve, that formula would be S of t. That's sort of what I'm saying. If I could somehow find a formula that gives me the area on any interval, it's actually giving me values of S of t. Right? The function would be equivalent to S of t. That's the whole idea. Yeah.
Isn't it the antiderivative of v?
S. The antiderivative of v is s.
Yeah, so but you go s.
The antiderivative
What's
of,
the
yes, this is
antiderivative?
right? V is the derivative of s, the antiderivative of v is s. This one. Right? In other words, if I take the derivative of the thing and I find the area, it's sort of like giving me back the original thing. Right? And it turns out the integral is what's going to give us the area, which is we're going to find out. So we're going to sort of use this idea to jump to the concept of, oh, the integral is the opposite of derivative, sort of. Right? So we've noticed all these curious facts for a long time, but it wasn't until the fundamental theorem of calculus that we could tie it all together and sort of see these things happening. So just wanted you to notice that curious fact. So I have a function, I take its derivative, I get another function. Somehow the area under that function can tell me about the original function. So if I can find the area of a function that tells me the area under a function, it can actually give me information on the original function. Right? Just like how the slope of this told me about that, the area under that can tell me about this. You see that they go hand in hand. Take the slope, I go in this direction. Take the area, I go in that direction. It's sort of like an inverse function sort of relationship.
So you got the area under that and you figured out how long you traveled?
Yep. Right? So this is a function, I take its derivative, it gives me the velocity. But then I take the area under the velocity, it tells me again about this guy.
That's the distance
This is
traveled?
the distance, this is the distance function.
Okay.
So this is sort of the end of 4.1. They had this discussion, and I thought I'd put it at the end, at the beginning, so you can sort of see.
So all we're going to do for Tuesday?
No, we're not going to finish this today.
When's the test?
Tuesday.
You're going to have a test with you, bro.
No, we have it be online. Well, the distance part of the chapter, it's really only this that they spoke about. They did this with more detail. We'll talk about the area. We'll start with the goal here. Fine. Let me say approximate. Let's start. Should I say fine? Let's say fine, and then we're going to say, well, we can't really find it exactly, so let's start with approximating. Let's go with that. This is our goal. We want to find the area under this curve. So here I have y equals x squared. I look at 1, and I look at 2. I want to find this area, right? That's the goal, right? So So, do you know a formula that gives you the area for a shape like this? Oh, no, an integral is not a formula for the shape of that. Okay. So the idea is.
Sorry. We're gonna find the area, right?
Yes, we're going to find the area. The thing is, the area, we know these sides are straight, and then this was curved, so it's sort of like we don't really know a formula for the area, so then we have to try to figure it out. Okay, if I want to find the area of this, what do I need to do? Well, the idea is to use what we know about finding areas to approximate it, right? So the idea approximates with areas of. So what are some things that I know to find areas of? Well, triangles, circles, rectangles, and all that, right? Which one of those would sort of fit with this? Well, the best one here would be rectangles. Sort of the one that lends itself here. So if I have this guy between 1 and 2, I don't know the exact area, but what I can do is I can use rectangles here, right? Just make rectangles under this.
Why would you do that?
Because I don't know a formula for that. But I know a formula for a rectangle. What?
Why are you doing so many small rectangles? Why don't you just do one big triangle?
Not this.
What?
Why are you doing so many small rectangles?
Because that makes life harder.
Oh.
Remember, our goal is also to come up with like a formula, a systematic way to do this. I'm not going to start mixing up shapes. If I'm using a rectangle, I'm going to stick with rectangles so I can have a system. Length times width, right? And I'm going to try to add these up. So if I put all these rectangles under it.
Professor, wouldn't it be better if you can use the right angle? Yes. This is right triangle like that. A hypotenuse on this side, right?
The hypotenuse can be curved. That's
What?
a curve, that's not a straight line.
Yeah.
Yeah.
He wants you to make it a triangle.
That's what I said, but it's curved, it's not straight. So it can't
Yeah,
be.
so when you have this, right, and you will have a little curve inside, on the bottom, right? And then you will, yeah, and you can use the secant and tangent to find the bottom part, right?
Okay, here's the problem with the triangles. Here's that, the thing with rectangles is they're really nice because you'll notice that if I put in more rectangles, I start to fill in all these gaps, right? Could you actually do that if you had right triangles?
No.
We'll put the little right triangle.
Yeah, right. So if I did this and I put a right triangle here, right?
Yeah.
Where would I draw the other right triangle to fill in this gap?
You see little space on the right triangle.
Too much
Huh? Where would you do it? Let me draw it there. You have this.
Yeah.
So you have one of the right triangles here, right? So there's all this gap.
Yeah.
Fill that in with another right triangle.
Now, we don't have to make, now let's make a similar triangle on that corner.
What do you mean?
Make a similar triangle like
It was,
that.
they want you to put a triangle in a triangle.
That's
not
a right triangle.
And then,
That's not a right triangle.
Let's change the triangle. Let's do it.
Still a
yes,
triangle.
no, it's not the same triangle.
So you have to use the same shapes all the time.
I want to approximate the area in some way that's easy, that I can have a formula for, where I don't have to be, okay, here's a triangle, let's flip it and stretch it, and then try to figure out a formula for that triangle. You know, it's too hard, right? But if I do this with rectangles, they're all the same formulas. They're very systematic. I can say, oh, I just add up the areas of all these rectangles, all these length times width, add them all up, I'm done, right? Right? And the rectangles actually give me a way where I can start to fill in these things. All I have to do is keep putting in more rectangles, and the thing will get small. But the difference between my approximation and the curve will become smaller and smaller. Right? Now, in theory, if we could somehow put an infinite number of rectangles under it, I could get the exact area. I'd fill in all those gaps. So that's the theory. So area under curve is approximately
question, find the area of all these edges. Can you find the area of these? Right, so you subtract. Professor, I was thinking of that. I was thinking like this. So we have a curve, right? We make a big rectangle, right? And we can find the area of these, right?
How? That's the curve shape under there. What formula do you have for the area?
Can you use like something tangent? I think we went over that. Like let's say tangent and the secant. That's the parallel line, right? Remember we did one lesson on that?
Yeah, that doesn't help us with area. That helps us approximate the tangent.
Oh, that doesn't. So that doesn't work with the area. I was thinking of that lesson, so I thought we could use that somehow too.
There are other ways to make curves under this, but we'll say that for Calc 2. For now, we're sticking to rectangles. Now remember, we want a system so that we can generate a formula to get a nice answer all the time, right? So it turns out we don't just want to throw rectangles under there, but we want to make it nice, right? So we want to make all the rectangles the same width, and then we want to decide how we're going to place them, right? So one way is the what's called the right-hand rule. Right, this is one way, right, where the top determined by the right side
Not that right.
Oh, well, maybe right-hand rules or right-hand approximations or something like that. No, we're not doing like electric fields and flux here. Okay, where it's like, so we have this idea of what we're going to do is we're going to split the interval between 1 and 2 into smaller intervals, right? Like for example, I could split it into 4, right? Or 5, but let's start with 4. And what I do is on each interval, I look at the right side, and that's where I draw the rectangle up to hit the curve. Yes?
How about trapezoids?
We can use trapezoids. That's again in Calc 2. That's called the trapezoid rule. Now, right? Yeah, there's trapezoid rule, Simpson's rule, all that. Right? So here in the right hand, I can keep just making my rectangles by taking the right hand of the subinterval, hitting the curve, and then coming over. Right hand, hit the curve, come over. Right, note, in this case, the rectangles give an overestimate for the area. Right? So if I add up the areas of all these rectangles, I actually get more than the area I need. Another way, though, I could have done it is to define the rectangles by the left side of all the intervals. So I have that same function. Now between 1 and 2, I cut it up into little pieces. And now I take the left side of the rectangles to hit the curve and define my height of the rectangle to be that. In this case, this is. So these are some of the things they could ask you. They could say, use the right-hand rule and the left-hand rule. Does it give an overestimate or an underestimate? Right? And it just depends. You have to figure out, is the area of all your rectangles under your curve or is it above your curve?
Oh, they're like different curves? They give us different curves?
Yeah, it's not, here I'm using x squared as an example. They could give you this with any curve. Yeah.
Oh, we need to subtract that from that.
Well, subtracting, well, there's one where you're above.
Yeah, and then the one.
If you subtract them, you'll just get the difference between this. It will give you the error in both your approximations. There's another thing called the midpoint rule. I mean, they call them the rules, but I don't want you to mix it up with physics, I guess. I didn't think any of you could take physics yet. Where here I use the middle of each interval. So here's my function, 2, 1, and 2. So I cut this guy into 4 pieces. And this time I use the middle of the intervals. And I make that where my rectangle's height is. So this goes like that. This goes like that. This goes like that. So you see here, so this part here gives me an overestimate, but then this side here gives me an underestimate, so it's supposed to be sort of more accurate. So you're sort of trying to balance things out. Right? So somehow I have this system. I can decide, okay, I'm going to cut up my interval a certain way and then use all the right sides to define the rectangles. Or I can cut it up and use all the left sides to define the rectangles. Or I can cut it up and use all the middle to define the rectangles. Right? So let's finish with this one example so you can see something right through. Use right-hand endpoints to approximate the area under 5 x squared with 4 subintervals. So let's see this here. 1, 2. If I want to split this into 4 subintervals, I want 4 gaps. What would the numbers have to be?
No, actually 1.
Huh?
You can,
Each would have to be, the distance here is 1. To get into 4 subintervals, I take the distance 1 divided by 4. So each distance here would be a quarter, right? So 0.25. This would be 1.25. This would be 1.5. This would be 1.75. Right? Now if I'm using the right side, I know this is the one I'm going to go up. Cut that off. Go up. Cut that off. Go up. Cut that off. So how would I approximate this?
we use the formula.
I have the areas of all these rectangles, right?
Yeah.
What are all these rectangles?
Rectangles are, which one are we using the right number? So first we find the changing x.
They're all going to be a sum of length times width. Right? So the width of all of them is 0.25 in this case. So it's 0.25, 0.25, 5, 5. Now the height of the first one is going to be what? How do I figure out the height of this rectangle? By the y value, right? The y value, all I have to do is find the y value corresponding to this point, And that's the height.
1.25 squared.
So this is going to be 1.25 squared. And this would be
1.5 squared.
1.5 squared. This would be
1.75
1.75 squared. This would be
2 squared.
2 squared. Right? In other words, I can have 0.25, I could have factored all these guys out. 1.25 squared plus 1.5 squared plus 1.75 squared plus 2 squared. Right? And if I get that number, it will give me something that's an approximation to the area, but an overestimate. So, do you sort of get the idea of what we're doing here? So we want to approximate this area, but we don't know how to find area under this weird shape, so we use rectangles because we know how to find areas of rectangles. So we systematically throw a bunch of rectangles in some interval, and then we add up the area of the rectangles to sort of approximate the area of the actual thing. But of course, it doesn't give us the exact answer. Right? But we're going to keep searching for one, and we'll start next week. Well, not next week. Next Tuesday we have a test, we'll start the week after. So this is just the beginning. I'll give you formulas. We're going to like come with formulas for all this and actually.
So we're not done with this, right?
No, we're not.
So we have test.